Welcome to your video on introducing concrete mix design. So when we're doing concrete mix design, we do something called the absolute volume method. And this has been developed by the Portland Cement Association, or the PCA. And you can actually see there's a number of steps. When we're doing the mix design, we would only do steps 1 through 10, not making the trial and test mixtures. But what we've done, because there's so many steps, and it's a step-by-step procedure, so your book has the steps in it, and I've also compiled a quick reference guide for you. And so what you'll see for step 1, where it says evaluate strength requirements, we have step 1, determine the mix strength requirements. And you'll see then that there's course text references. There's also PCA handout references, because since this does come right from the PCA, Portland Cement Association handbook, and that will be uploaded for you to look at on the Camino site. And then there's some really important comments on this quick reference sheet, and you want to make sure you read those because they give you tips, hints, tricks of when things could get tricky and when you better read the texts or paragraphs that go with certain tables, because it's not just about going to the tables. You might have to modify values in them. So you will definitely want to be referencing your textbook for the tables and what you need for the mix, and then an activity sheet. So pause the video and grab this stuff now. Right, now that you're back, let's look at the problem that we want to solve. So we're supposedly designing a loading dock that's 12 inches thick slab, and it's going to be in an area that experiences freeze thaw. We have an engineer of record that has requested a 4,600 PSI design strength that they are counting on to say carry the loads that are going to be on the loading dock. And it turns out that we actually have a mix as the batch plant firm that's going to be making this concrete mix. We've made this mix about 21 times, so we have some trial batches, and we do have some data about this. Now, we have some information about the available materials, so air entrainer that we're going to be putting in to add those tiny bubbles to help with freeze thaw and workability, coarse aggregates and fine aggregates that we plan to use for this mix. Now, here's the deal. If you're making a loading dock, you're going to need a lot of concrete, maybe 8, 9, 10, 12 yards, cubic yards of concrete. I don't know how big the dock is. But when we do the design, we always are making 1 cubic yard, or 27 cubic feet. That's the volume that this absolute volume method will result in. If you need more or less, you simply then scale the results. So step 1, we need to figure out, based on the requested strength, what should the required strength be. When we're dealing with mixing concrete and variations in the aggregate and mix time and etc., you're not always going to get exactly 4,600 pounds. And in fact, we see in this case, we had 21 trials, and in those 21 trials, from the mean of 4,600 PSI, we varied by 270 PSI above or below. And so as the engineer, I'm going to want confidence that I'm going to get a minimum of my 4,600. I can't be down at 4,300 because I was at the lower end of the standard deviation. That could really mess up my structural calculations. So what the PCA did is they used probability and statistics, and they looked at creating a normal distribution and said, okay, let's put the peak load that we're going to target, which is higher than what we need. And they said, okay, look, here's F prime C. This is the requested strength. We're going to have a required strength that's actually going to be our target that'll be higher. And if we take the standard deviation S, multiply that by 1.34 from this normal distribution curve, we can see that 90% of the time we can feel confident we're going to exceed F prime C. So we're going in with a 90% confidence interval. So they've created this equation. If your standard deviation, this is equation 7.1 in the text, if your standard deviation is less than 500, you can just use this normal distribution. If you have a larger standard deviation, so even more variation, then we actually have a second equation that we would use, and this is equation 7.2. And remember, using your quick reference guide, it tells you you can use tables 7.1 or equation 7.1 and 7.2, but then with these additional tables, and you want to be reading page 274 and 275. Now, what these additional tables are about is that, say for this example, we've made 21 batches and know our standard deviation. Would you feel more confident if you had made 100 batches? Would you feel more confident or less confident if you'd only made 5 batches, right? The number of batches you make really tell you how confident you should feel in always getting to a set number. And so what happens, if our number of trials isn't very large, we actually have to increase the standard deviation. So what we'll see, if S is based on less than 30 samples, then we do have to increase the standard deviation. So if it's 30 or more, we don't. If it's only 15, we have to increase it by 16%, and you can see some other values, and we just interpolate to get our modification factor that we would increase the standard deviation by. But here's the deal. Notice that this table starts at 15. If you are less than 15, you are not allowed to use equations 1 and equation 7.2. In fact, what you actually have to do is use a very conservative formula. And so let's take a close look at this. So there is no multiplication happening in these tables. What we see is any values that are worked in megapascals are going to be the ones outside of parentheses, and then anything in parentheses, or if you're working in SI units. So for our example, let's say we only had 5 samples, but we still wanted the 4,600 PSI minimum guaranteed strength. Well, we'd have to come in and say, okay, the specified requested strength is between 3,000 to 5,000 because it's 4,600. So then we come over here and we say, okay, well, 4,600 is our requested. We have to add 1,200 PSI to that. So then the required strength that we're going to design for is going to be 5,800, the 4,600 plus 1,200 PSI. So that's super conservative, right? That's way higher than what we were requesting. So you can imagine how much more cement, aggregate, everything that we're going to need. So this is not a sustainable or economical method. So if you're doing very large projects, you wouldn't want to do this. You'd literally, it'd be more cost effective, more sustainable to go and do 21 batches, test batches, and try stuff out, get the mix you want, and then design it. So let's look back then at our project. So we've said we've got 4,600 PSI, we have 21 trials with a standard deviation of 270. So that means if we look at our step 1 and we look at our textbook, we can actually use equation 7.1, but we have to use a modification factor because we don't have enough trial batches. So with 21, we end up finding our modification factor is 1.07. And so we take our 1.34 times our standard deviation, we've increased by 107, and we add that to our 4,600. Now, we end up with a number around 4,962. You would never use something to that specificity. We always round to the nearest 10 PSI, so you're going to report 4,960. Now, if you're not sure how to interpolate, there's how I got the interpolation value, and you're welcome to pause the video and stare at that and figure that out so that you can see how to interpolate. So now we're ready to move on to step 2. So step 2 is that all critical water to cement ratio that we know is super important. So to figure out the water to cement ratio, typically your large concrete batch plants are going to use historical data, because not only have they maybe done 21 tests on a sample to get 4,600 PSI concrete, but they've done 50 tests to get 44,000 PSI or 70 tests to get 3,500, etc. And so they're going to create strength curves. And so again, using your step 2, it tells us you're going to use figure 7.3 and table 7.3 and 7.4, and we'll come back to what 7.1 and 7.2, these tables are about. Now, what a strength curve looks like is something that says, okay, for a set water cement ratio, what sort of strength, either in KSI or megapascals, can I expect? Since in the course, we're not a batch plant, we don't have a bunch of historical data, we're going to use figure 7.3 for the whole course and assume this is our historical data that we get to work with, right? So literally we want to just come in, we're on the KSI side, we have 4.96, and we're going to draw an arrow over to our strength curve. Now in this case, we said we are adding air entrainment. We want to add those tiny bubbles because we're in a freeze-thaw zone. And my arrow might be a little low, but it's fine for this example. And obviously, hopefully a company has a plot that is much more detailed and delineated. But I then just drop down an arrow, and I'm going to say that I'm at a water to cement ratio of 0.42. So that's my starting point, but remember, we also must verify that this water to cement ratio does not exceed the allowable values from table 7.3 and 7.4. Now, if you do not have a historical curve, if you don't have any data, that's when you use table 7.1. And so 7.1 literally is what's my project about, what's my job about, and the Portland Cement Association suggests a water to cement ratio to start with, and then you actually make a bunch of trial batches and you test them, okay? And that's what you're gonna do when you have a large job. Now, if you have a really small job that you're doing, say you're just pouring a driveway and it doesn't have to be critically strong, then you can jump into table 7.2 and use the water to cement ratios in that table. It, again, is just more conservative. But since we have our historical curve, we can now look at table 7.3 and 7.4 to make sure that we're meeting the water to cement ratios, the minimum values in those. And so the tables are about exposure conditions and sulfate exposure. And once we find all the water to cement ratios, we want to use the lowest because that's, we know, is going to give us the strongest concrete with the least pores from water evaporating. So here's table 3. It's all about exposure, typically to freeze-thaw type cycles, de-icing chemicals, that sort of thing. And so what we had is we said we have concrete that's exposed to freezing. We do not have de-icing chemicals, but read this clearly. It says or, not and. So either de-icers or freeze-thaw. And we see that we need a minimum of water to cement ratio of 0.45. Well, figure 7.3 gave us 0.42, that's even lower. So we're definitely meeting this requirement. So we want to write down that we need 0.45 from table 7.3, but check, we'll meet that. Also though, notice, and this is important, is that the PCA has also established some sort of minimum guidelines if you do have concrete that's going to be exposed to extreme weather and chemicals. And so they're saying for this condition, you better have an initial strength requested, F prime C, not F prime CR, of 4,500. We have 4,600, so we're okay. But if the engineer of record had specified 4,000, we'd have to start over at 4,500 and do our equations again to get the F prime CR, the required based on a minimum of 4,500 and the guarantee we get there. When we look at table 7.4, this is just if you have concrete that's exposed to sulfates. We don't. In this class, you will be told in your problem statement whether or not sulfates are there and if it's a moderate, severe, very severe. And so for us, this is not applicable, right? So what that now tells us, we checked 7.3 figure, table 7.3, table 7.4, and the lowest water to cement ratio that we came out with was 0.42. That is going to be our water to cement ratio that we're going to move forward with. So now we're ready for step 3. So step 3 actually has 2 parts. So when we look at this, there's determining, if we look in our quick reference sheet, determining the maximum allowable size of coarse aggregate that we can put in. And I just noticed the typo on the word coarse. And then the bulk volume of coarse aggregate per unit volume. Yes, this is not the class course. It should be an A. To figure out the maximum allowable size that we can put in, we need to be looking at the formwork, the rebar, that sort of thing. Because if we remember, if we're pumping, right, we want to fit through a pump, and then we have the formwork, we have the rebar spacing, and the aggregate has to fit through all of that. And that's what this first step in step 3 is about. And so if we look, we have a slab thickness of 12, so that's kind of our formwork, right? Top to bottom, where the ground to the air. We're going to cover the concrete with at least 3 inches, so that, or any rebar with at least 3 inches, so that's going to be our distance from, say, the ground to our rebar, so that's our formwork spacing. Our rebar is 1/2 inch diameter, or 4/8, 4/8. And then a minimum distance of 4 inches between the rebar, because the rebar is spaced at 4.5 on center, but each bar is a 1/2 inch diameter. So obviously the larger size aggregate we pick, the less cement we need, because the aggregate then takes up more volume, and that then brings our costs down. But we do have to fit into the spacing. And so you'll find this table on page 279. And so our form dimensions, what we're looking at, that in our case is our slab thickness. And so we need 1/5 of that minimum clear distance. Our clear space is 12 inches, so it would be 1/5 of 12, 2.4 inches. Clear space between reinforcing, in our case, we saw that that was 4 inches. So the maximum aggregate size has to be smaller than 3/4 of that, or 3 inches. And then the clear space between the reinforcement and the form, and we saw that we're going to have 3 inches of cover over our concrete, so say from the ground to our rebar, so 3/4 of that, which is 2.25 inches. And all of that has to be larger than the max aggregate size in your mix. Not the nominal MSA, but the MSA. And if you don't remember the difference between the nominal max size and the max size, go back to page 1 of chapter 5. We've already covered this in aggregates, and look up the difference, right? So right now, 2.25 was the smallest as we did this math. And so when we go back and we look at our available materials, we see, we're told that the batch plant plans to use a max size gravel of 3/4 of an inch. So we're good to go. You'll also see that there's some additional information here. We're told what kind of gravel, and that's going to come into play in determining how much volume you need of water. We're given the oven dry specific gravity, and specific gravity, we know unit weight of water over the unit weight of the object over the unit weight of water. The absorption, so that moisture content at saturated surface dry, the oven dry rotted weight, and then the moisture content that it's currently in. We have the same basic information for our fine aggregates. We have our specific gravity, our absorption, our moisture content, and then the fineness modulus of our fine aggregate, and that's going to be important in our mix design. And then recall, we want to put in air entrainer, and so we are given the formula from the manufacturer that for every 100 pounds of cement that this mix design method ends up telling us we need to create 1 cubic yard of concrete, for every 100 pounds of that and every 1% of air that we put in for air entrainment, we're going to get back out, or we need to put in 0.13 fluid ounces of their material. So to this point, you should on your worksheet have figured out steps 1, 2, and 3A, and I'm going to really recommend to you that you take the time and you write down, like I've done here, where things come. I have 21 tests, 270 psi, so I get to use equation 7.1 with the modification factor, so that you have a roadmap when you have to go create your own mix designs for what to do. Noting table 7.1, 2, and 4 not applicable, but what do we get from 7.3, 7.4, which one controlled, right? So step by step, create a roadmap as you're going through this. So now review steps 3B through 8. Use that quick reference guide. Look at the text carefully to see what's in there. Try to figure out where your questions are. Come to class prepared to work with classmates to complete these steps. Thanks for watching.